When you go to the grocery store to buy eggs, you typically don't buy individual eggs. Most often, they happen to be grouped into a dozen. In everyday English, the word dozen simply represents the number 12 as a quantity. Thus, it has no unit, and it can be used to quantify any object you want, such as the number of eggs. But when you're dealing with atoms and molecules, you are dealing with objects so tiny that it makes no sense to count individual particles or even dozens of particles. Instead, just as grocery shoppers use the word dozen, chemists use the word mole, which represents the number of carbon-12 atoms in 12 grams of carbon. This number is around 6.02 times 10 to the 23rd power. This number is also known as Avogadro's number, which we give the symbol capital N sub A. So the number of carbon-12 atoms in 12 grams of carbon is Avogadro's number. The number of moles is given the symbol lowercase n and represents the amount of any substance, not just carbon-12 atoms. We can therefore derive some simple calculations. Since there are 6.02 times 10 to the 23 particles per mole, the total number of particles should equal the number of moles multiplied by 6.02 times 10 to the 23rd. Using symbols, we write this as capital N, which is the total number of particles, equals lowercase n multiplied by capital N sub A. Let's do a few standard high school questions to get the hang of this concept. How many particles are in 4 moles? If 1 mole of particles is equal to 6.02 times 10 to the 23 particles, then 4 moles should be 4 times 6.02 times 10 to the 23, which gets us a product of 2.41 times 10 to the 24 particles in 4 moles. How many moles of a particle are in a certain number of particles? For example, suppose we have a small container of water and we are told that it consists of 3.01 times 10 to the 25th power water molecules. Using basic algebra, we can calculate the amount of molecules to be equal to the number of particles divided by Avogadro's number. This gets us 3.01 times 10 to the 25th power water molecules divided by 6.02 times 10 to the 23rd power molecules per mole, which is 50 moles. This question is just like asking, if you are given 48 eggs, how many dozen eggs are there altogether? So far, we've calculated the number of discrete particles. But what if we're interested in smaller units like individual atoms or ions? For example, how many carbon and oxygen atoms are there in 1/10 of a mole of carbon dioxide? First, how many carbon dioxide molecules are there in 1/10 of a mole? It must be 1/10 of Avogadro's number. So there are 6.02 times 10 to the 22nd power carbon dioxide molecules in 1/10 of a mole. So how many carbon and oxygen atoms are there in this amount of carbon dioxide molecules? For each molecule of CO2, there are 1 carbon atom and 2 oxygen atoms. So 1 mole of CO2 molecules gives 1 mole of carbon atoms and 2 moles of oxygen atoms. Given the atom-to-molecule ratio, there should be just as many carbon atoms as there are carbon dioxide molecules. The number of carbon atoms is 6.02 times 10 to the 22. And there are twice as many oxygen atoms as there are carbon dioxide molecules. The number of oxygen atoms is 1.2 times 10 to the 23.